Hello friends, welcome to our channel. Let's have a look at problem 3489, Zero Array Transformation 4. In this video, we are going to solve this problem using dynamic programming with bitmask. So we are not going to read through the problem statement, but I want to mention to you the problem size, which is determined by the first 3 bullet points. And then the last 3 bullet points are some consistency assumptions. So with that said, let's look at some notions. So here I'm going to use n to represent the length of this nums list. So a typical element in queries is this L, R, and value. This gives the first 2 elements gives you the range. So the value gives you the decrement amount. So here the DP initialization will be the following. So we'll have a length n 1D array. So initialized as 1. The DPI is interpreted as the decrement amount nums I can get. So if a bit position p is set, it means nums I can decrement amount p. So in the DP initialization here, for each index I, so we initialize as 1, in which the 0th bit is set. It means that each nums I can get 0 decrement if we do not use the queries. So this explains the initialization. So now let's look at the DP update. So for each query, so here I'm iterate over a query. I want to check up to which query we can make all the nums elements to be 0. So for each query in the queries, so iterate over the indices j from L to R inclusive. Then dpj would be dpj because the original state encode the amount we can decrement. Then shift to the left, this amount means that from the original amount we can also decrement this amount. So this is bitwise OR. In terms of set, you can think of this as a union of sets. So actually we are going to make a video using all the possible sums up to a query to address this problem. So this is an extension. Okay, let's come back. So this yields all the possible decrements for elements in nums. For example, if the jth position, this position, bit position, is set, the position index is nums j, right? If this is set, it means using the query up to now, we could decrement this dpj to be 0. So during the iteration over query, once we found for all nums j, right? So if we have this condition holds, it means we could make the whole array being 0. So we just need to return the number of queries we used up to now, right? So this will be our main idea. So now let's do the coding so that you can have some better intuition. Then you can come back and forth to compare the code and the 2 items here. So first I want to do a check. So if all, so for y equals 0 for y in nums. If this is true, we just need to return 0, right? We don't need any array because initially it's a 0 array. Otherwise, let's have this n to denote the length, and then initialize the dp table. Next, I'm going to iterate over the queries. So for I, L, R, and value in enumerate queries. So notice that we need to track the index, so we use enumerate. So this is the generic element in queries. So here in tuple format. So then we want to iterate for j in range L, R plus 1. So here we write R plus 1 because we want to include R, right? And then the dpj will be dpj shift to the left this amount. So I'm going to add some parentheses. Sometimes it might be unnecessary, but I don't want to think too much or remember the operator precedence in Python, right? So then we know that for dpj, we we need at most, nums g plus 1 and bit positions, right? So in terms of decimal, so this 2 to the power this one, nums g plus 1, so will be the actually minus 1. So I'm going to add a parenthesis minus 1, because plus and minus is higher precedence than this shift operation, right? You need to use this parenthesis. Actually, this parenthesis is necessary. So for example, if you want to use 3 positions, then the corresponding number is 2 to the power 3 minus 1, 7. 4, that's 2 to the power 4 minus 1, 15, right? This is exactly here. So this way, they can restrict the size of DPG. We don't want to make it too large. In other words, if nums g is greater than 0, so if there's 0, so set just beta is 0 right here. So what we do is dpg, so we do bitwise add with this number, so with this number here. So notice that this parenthesis here and here is necessary, otherwise it should first minus 1. This is not what we mean, right? So once we have this, now we do a check. So in order to make it more clear, so you can actually use a list here. So this is more clear, but still you don't need, in a rigorous sense, this. So what we want to check, if this bit, so dpg, if this bit nums g is set, right? So we do bitwise add with respect to 1 for g. So actually, in order to distinguish with g, so I can use say t for t in range n. So if this is true, it means that we can make every element in nums to be 0. Then we just need to count how many arrays we have used, that is I plus 1. So if after this for loop, nothing has returned, so we're going to return -1. So this will be the full code for this problem. Now let me first run it. Count assign to function called, let's see, dpt. So here, t, right? So dp t, this one for t in range n. So count assign. Let's see. Let me change this one, make it for sure correct. This is the for. I should say if, right? So for all, so this will be dpj, let's see, right? T, nums t, add 1 for t in range n, right? It's not a for, it's a if. So let's check. Yeah, it passes all the cases. Now let's look at the generic case. It passes all the cases. Let me submit again to make sure. Yeah. So this is the one version of the solutions. So here I first iterate over the queries. So once up to a query, we can make all the elements in nums 0. We return the count. So actually, you can also first iterate over nums. So for each element in nums, what's the minimum amount of query you need, right? So then we just need to return the maximum amount among those. So let me write another solution. So here, let me call this one version v1. So now in here, what I want to do, so what I'm going to do is iterate over nums. So for each element, say y in nums, check how many queries we need to make it 0. So how many here should be the minimal, right? Minimal amount. And then we take the max of this minimals. So we will get the return. So the idea will be the same as we explained here, but for completeness, I also want to code it here. So for this, we can initialize an answer that's 0, right? And then what we do is this. So we are going to, for I, x, in enumerate nums, right? So we want to check for this element. So how many queries we need. So if x equals 0, we don't need, right? So we just continue, right? And then we're going to check, we're going to use a flag or bitmask. So let's use this as 1, right? So then we're going to iterate over the queries. So, so in the first version, we iterate over query and then check all the inbound indices. But here, let's do this. So for key, L, R, and value in enumerate, so queries. So what we want to check is that if not, this one, L less than equal than I less than equal than R. If the index I is not in the range of this query, so we continue. So otherwise, so we update this F to be F shift to the left, this amount. So this is in parallel here, right? And then what we do, so we are going to check if F shift to the check if this bit at bit position X is set. If this is set, so we are going to update the answer. So then up to this key, we can finish this X, right? So this X need, so basically it will be max of the previous state, and for this X we need key plus 1 queries because key is the index starting from 0. Then ending at key they have key plus 1 queries. Then you are going to break, right? Then here after, if the for loop can finish, then what we want to do is we are going to return -1, right? So you need to be familiar with this for else block in Python. So if the for loop can finish smoothly, then it's going to enter this one. If you have a break, then we will not enter this else block clause. So this will be the same as here, but just switch the order, right? So now afterwards, you just need to return the answer. Now the answer actually is exactly here, right? So for each y or x, so we compute the minimal queries needed to make it 0. Then we take the max of these minimals to get the return. So here, for each x, so we get the answer if we can, right? And then we compute max. So finally, you get the result. So if for one element, after you use all the queries, you still cannot make it 0. And then, so you are going to enter this else block clause, you directly return -1. So this is actually a way of early stopping. So with that said, I guess let's check the second version. Yeah, it passes all the cases. Now let's submit. This is also very fast, I guess. So with that said, I guess that's basically about it for this video. So in the follow-up video, we are going to do an extension. So essentially the extension will be the same as the two solutions here, but the idea is here. Another way to address this is that when processing the queries, we monitor for each index. So the index is in this range. What are the corresponding decrement amount possible, or we can construct. So then we just need to check. So basically we will get such a dictionary for each index. So the corresponding possible decrement amount. Then if for all these i's, so nums I is in di, it means that we could make all nums to be 0. Then we just need to return how many queries we used. So this way actually is identical to the version we want here. But we use different representations. So here we use this DPG, or use an integer to encode all the possible sums. But it's also interesting to construct explicitly all the possible sums up to an index at each for each element or for each index, right? So this will be our task for next video. You're welcome to follow up. So with that said, I guess that's it for the current video.